Students, in today's class we will learn how to solve integral 0 to 1 sine of ln z divided by ln z times dz. Now z is just a variable, right? So it has got nothing to do with the complex variable z. So this z is just a z there. In other words, this is a real quantity. Now we know that sine theta has an expression e raised to the power I theta negative e raised to the power negative I theta divided by 2 times I. Now when theta is equal to ln z, I can rewrite the entire expansion or expression to be as sine of ln z is equal to e raised to the power I times ln z negative e raised to the power negative I times ln z divided by 2 times I. Okay. Now we know from logarithm that ln a times ln b can be rewritten as ln of b raised to the power a. Now using this, I can rewrite this as e raised to the power ln of z raised to the power I negative e raised to the power ln of z raised to the power negative I divided by 2 times I. Now this is e, this is ln z. Okay. Now we know that the e and the ln, they get cancelled. So that would mean we now have z raised to the power I negative z raised to the power negative I divided by 2 times I. This is what we have got for what? For sine of ln z. Now I am going to be using this expansion for sine of ln z into the given problem. So if I were to use this expansion in the question, I can rewrite this question to be as integral 0 to 1 z raised to the power I negative z raised to the power negative I divided by ln z. I've got a 2i there, you place the 2i there, and that has to be multiplied with dz or dz. Now I want to define a new function. Okay, so let me define a function called as I of t to be equal to integral 0 to 1 z raised to the power ti negative z raised to the power negative I divided by 2 times I ln of z times dz. Now when t is equal to 1, I would have I of 1 is equal to integral 0 to 1 z raised to the power t is equal to 1. So that's going to be I negative z raised to the power negative I divided by 2 times I ln z times dz. So if you were to see the quantity here, this is exactly I of 1. Okay. So that I of 1 has been obtained from the function we have defined. Okay, so we have defined this. Now the question is, we have to find what is I of 1 equal to. If we can do that, then the solution is complete. So how are we going to do that? We are going to do that from this function which we have defined. Now how are we going to do is that we are going to differentiate this quantity both sides with reference to t. So d over dt of I of t is equal to d over dt of the integral 0 to 1 z raised to the power t times I negative z raised to the power negative I divided by 2 times I ln z times dz. Okay, so this is t. Now this quantity, the integrand, is continuous and it is convergent. Because of this fact, I can interchange the differentiation and the integral operators. Now I'm going to move this d over dt inside. Now you have to understand one thing. I've got a t and a z, so two different variables are there. So this complete differentiation or total differentiation would become partial differentiation. So this is going to be 0 to 1. When d over dt comes inside, it will become dou over dou t of z raised to the power ti negative z raised to the power negative I divided by 2i ln z times dz. Now what I'm going to do is I am going to be applying the partial differentiation. Now clearly this is t and this is t, but this is basically treated as a constant because of the partial differential nature. So this is going to be rewritten as 0 to 1. I'm going to take 1 over 2i times ln z out and bring dou over dou t inside. This is z raised to the power t I negative, so let me just write it like this, negative dou over dou t of z raised to the power negative I, and this as dz, the operator. Okay, now you have to know a very important formula. Now differentiating, say, x to the power 3, I would get 3 times x squared. Now if I were to differentiate 3 raised to the power x, then the differentiation would be 3 power x times ln 3. This is the standard formula. So now I need to differentiate dou over dou t of z raised to the power ti. So t is my operator. In other words, dou over dou t is the operator, t is the variable that with which we are going to be differentiating. So it's a functional variable. Now similarly, x is a variable here, t is a variable here. So we would get, upon differentiation, we would be getting z, okay, z to the power of ti, and then that has to be multiplied with ln z. Now there is a coefficient I with t, and that has to be differentiated. In fact, differential of ti with the coefficient I would give us I here. So this is what you have to write there. Okay, all based on the formula. The only addition that we see here is the presence of the coefficient I, which is occurring with t. So this is rewritten as integral 0 to 1 over 2 times I ln z, open the parenthesis, you write this quantity z raised to the power ti times ln z, and there is a I there, write the I there, negative. Now this is a constant and this is the variable with which we have to differentiate, that's going to be 0, okay, times dz. Now I can rewrite it in the following fashion. So that is going to be equal to integral 0 to 1. Now this is z raised to the power ti times I times ln z into dz divided by 2 times I times ln z. Now clearly ln z can be cancelled, I can be cancelled, and that would give me 1 over 2. Okay, but we have to write 1 over 2 out so that it can be treated as a constant. Of course, a constant. Now limits are 0 to 1 and the integrand is z raised to the power ti times dz. Now we know that integral x power n times dx is x to the power n positive 1 divided by n positive 1, positive arbitrary constant c. So by using this formula, this is going to be rewritten as 1 over 2 times z raised to the power ti plus 1 divided by ti positive 1. Now z is our variable, ti is just a constant, so that's why we are getting that. Now the limits are 0 to 1. Okay, so I substitute the upper limit, and this is a constant. Okay, so we need to substitute the upper limit. So I can write this as ti positive 1. It's a constant. Now I substitute the upper limit. So it's going to be 1 raised to the power ti plus 1 minus 0. Right? Now this is going to be giving me 1 over 2, 1 raised to the power ti plus 1. That's going to be 1. So what we are getting is 1 divided by 2 times ti plus 1. This is what we have got. Now on the left side we have d over dt of I of t. Now differentiating this would actually give us I dash of t. Okay, this is what we have got. But we don't need I dash of t. We need I of t. So how do I get it? Simple. We have to integrate the entire process. So integrating we get, on the left side it's going to be I of t. On the right side it's going to be integral 1 over 2 of ti positive 1 times dt. I can rewrite this as 1 over 2 integral dt divided by ti positive 1. Now if I were to take ti positive 1 is equal to sum u, this is going to be dt times I is equal to du, which is nothing but dt is equal to du divided by I. If I were to substitute that, that's going to be 1 over 2. In place of dt, I substitute du divided by I times, in place of dt I positive 1, it's going to be u. This is going to be 1 over 2i integral du divided by u, which is 1 over 2i ln of u, which is rewritten as 1 over 2i ln of ti positive 1 for u, positive arbitrary constant c. So on the left I've got I of t. Now what is I of t? I of t, we defined I of t as follows, right? Now I of t is integral 0 to 1 z raised to the power ti negative z raised to the power negative I divided by 2 times I ln z times dz. Okay, this is my I of t. So we need to know this arbitrary constant c. So if I were to take this as 2, so therefore 2 can be rewritten as integral 0 to 1 z raised to the power ti negative z raised to the power negative I divided by 2 times I ln z times dz on the left. On the right I've got 1 over 2i ln of ti positive 1 positive arbitrary constant c. Now I need to get the value of c. The only way is to make this quantity to be as 0. That is the only possibility that we have got. And this quantity can become 0 when I take t to be equal to negative 1. When t is equal to negative 1, we get integral 0 to 1 z raised to the power negative I negative z raised to the power negative I divided by 2 times I ln z dz. Right? Are you seeing it? This is positive z raised to the power negative I. This is negative z raised to the power negative I. So on the right, it's going to be 1 over 2i ln of ti plus 1 positive arbitrary constant c. So this would be 0. So that means I've got 0 is equal to 1 over 2i ln of ti plus 1, positive c. Now, actually, I have taken t is equal to negative 1. So I need to make the substitution t is equal to negative 1. So I would move it here and then I would place t is equal to negative 1. So that's going to be negative 1 over 2i with t being equal to negative 1. This is going to be 1 over 2i ln of t is equal to negative 1. So I can rewrite this as 1 negative I is equal to c. Okay. So this is the value for c. So now we need to club everything together. So how do we club everything together? All we need to do is take the value of c and substitute it in this system. So I will take this as, say, let me take this as 3. So therefore 3 would be rewritten as, of course on the left we know it's going to be integral 0 to 1 z raised to the power ti negative z raised to the power negative I divided by 2i ln z times dz is equal to 1 over 2i ln of ti positive 1. This is negative 1 over 2i ln of 1 negative I. Okay. Now I can take 1 over 2i common, but before that, now this is actually I of t, but we don't need I of t. We need when t is equal to 1. That's the requirement for the question. So when t is equal to 1, we get I of 1 is equal to integral 0 to 1 z raised to the power I negative z raised to the power negative I divided by 2 times I ln z times dz is equal to 1 over 2i ln of t is equal to 1. So this will become I positive 1, but this is 1 minus I. So I'm going to write it as 1 positive I negative 1 over 2i ln of 1 negative I. Now I can take 1 over 2i out, so that would give me ln of 1 positive I negative ln of 1 negative I. Okay. Now there is a formula. Now ln of a negative ln of b is ln of a over b. Okay. Now by this formula I can rewrite this as 1 over 2i of ln of 1 positive I divided by 1 negative I. I can rewrite it like this. Now I'm going to reduce this quantity by using complex multiplication, right? So that would give me, now you can just consider this 1 positive I divided by 1 negative I. You multiply by 1 positive I. You divide by same 1 positive I. This is going to be 1 positive I raised to the power 2. This is going to be 1 negative I squared, which is going to be, you expand the numerator, you get 1 positive 2 times I, positive I squared, that's going to be negative 1, divided by 1 negative of negative 1. Now this is going to be plus 1 minus 1 gets cancelled. You are going to get 2i in the numerator divided by 2, which is equal to I. So this entire quantity which you see here, it's actually ln of 1 positive I divided by 1 minus I. This can be rewritten as 1 over 2i ln of I. Okay, now ln of I has a value as pi over 2 times I. So if I were to substitute that, that's going to be 1 over 2i times pi over 2 times I. Now the I that you see here in the denominator can be cancelled with the 1 in the numerator, giving me pi over 4. Now this implies integral 0 to 1 z raised to the power I negative z raised to the power negative I divided by 2 times I ln z times dz is equal to pi over 4, which is the solution for this question. Thank you, students.